All right, hello. Good morning, because I tend to mentally live in like Icelandic time zone, so for me it's morning. Today I'm gonna talk about few ways to about how can you do machine learning in .NET, and let's start about me. I come from Tree City in northern Poland, but a few years ago I moved to Sweden to work for Triton37 company. We're a consulting company based mostly in Sweden, although we've opened our first office in Slovenia last month. We're a consulting company, but our motto is creating value by sharing knowledge. We like to do knowledge events for our customers and our community. We speak at conferences, and in fact we've been speaking at Dev Day and DevConf every year since 2012. So it's a good tradition we like to keep up. And for today, the end will be sometime around 6. We'll see how we're going to do with the time. It's going to be like general overview of how you can do machine learning or .NET. I'm not going to dig deeply what is machine learning, although I'm going to do some small primer. Just to scratch the surface. You shouldn't really get your knowledge what is machine learning from this few minutes, but I want to just put us on one page, and then we'll just go to like different ways to do it on .NET in 2018. So let's take some simple example. We have apartment prices, and they tend to depend on the surface area of the apartment. So the bigger apartment, the bigger price of the apartment. Of course, there are different factors to it also, but for this sample, we're just gonna focus on this one feature of the apartment. So we have like two-dimensional data, because the more features you add, you have to do like more dimensions of calculation, and it's getting pretty hard to visualize over 3 dimensions. So we just stick to one feature, so surface area. And the model I'm going to use is probably one of the simplest machine learning models. It's called linear regression. And basically, it's all about passing linear function to shape your data. And the linear functions are described by two arguments, W and B, or A and B, depending. This is like school math or machine learning. In school, it was Y equals A times X plus B, but in ML stuff, they tend to use W, because W stands for weights, so how important is the feature, and B stands for bias, so this is like some undescribed portion of information that you add to give better shape of the data. And to fit the data, you have first calculate how bad you are with this initial value, and just start with just straight line going through the middle of our Cartesian surface, and using this very simple cost function, calculate how bad we are. What this function does is basically takes the distance of your current data points from the initial line we took and average that distance. This gives us this is called mean squared error, and gives us kind of measure of how far we are from the best solution. And the way to get to this big solution, like one of the way to do it, is gradient descent. So basically, you find values of W and B that will give the lowest cost. So you'll have to kind of follow down this imaginary ball to find the best parameters to have the lowest cost value. So that function is like much better fitting to our data. It's not going to be ever perfect, because linear models are not very good for data, but it's gonna give us some approximation. So let's say we found a regression model using gradient descent. We found that the perfect formula for the price of the apartment is 5,000 times the square meters plus 20,000. So let's say we have, and that's our trained model. That's our linear regression model. And the second part in machine learning, first you have to learn the model, and then it's like inferring this model, so using it in like practical application. So now, let's say you have an apartment to sell, and you want to figure out what's going to be a good price to put it on the market. So let's start with like 40 square meter apartment. We feed to our function, we get 220,000 money, zlotych or whatever, and that's kind of approximation what's going to be a value of this apartment on the market if we only take surface into account. As I said, it's not that simple, but in real life, but we're just making some simplified model. And usually in real life, the like polynomial functions are much better fit for real life data. So the functions are much more complicated. And one way to get those polynomial functions is neural networks. A lot of people use like kind of brain cells connections intuition for describing what a neural network is. But for me, this analogy is quite harmful the deeper you go, because it doesn't hold very well. I like to think about it you just feed very complicated functions to the model of your data, and that's what neural networks give us. But we're not going to talk about neural networks today. It's a topic for a different talk. I'm going to move now to the ways to do machine learning. And currently, the most popular ways to work with machine learning models are around Python solutions, like TensorFlow, Keras, scikit-learn, PyTorch, and so on. And this comes from the fact that Python has been very good with tabular data, with numbers, with vectors. And this is the kind of operations you do on a regular basis to calculate machine learning models. And that's been the leading solutions. But if you, for some reason, don't want to learn Python, even though you still should, in my opinion, it's a very nice language, I prepared this kind of overview of what's available on .NET these days. So let's start from like the most crude way. It's like coding it all from scratch. You can write models from scratch. So you can write your prediction model, which is like the wx plus b function. You can write your cost function and calculate derivatives for the values and do like manual gradient descent. And you have to do it for like every dimension. So with one feature, you have 2 dimensions to calculate. If you have like 400 features, you have to do over 400 dimensions to calculate. So it's getting pretty annoying to do. But you know, to do something simple in 2 dimensions, but to understand how it works, it's like one way to do it. We calculate derivatives because the way gradient descent works, you kind of calculate derivative to know into like what direction that ball you have to go, and you have to do it like for 2 dimensions to find like the vector for 2 direction. And that's the actual learning. You do some number of steps. For each step, you calculate derivatives to get you to the middle of the ball. You make small steps and you repeat. And that's for this model to do like linear regression in F# on 2 dimensions. It takes around 100 lines of F#. It's probably a bit close to 150 of C# because some things are a bit less simplified doing C#, but it's totally possible, and it's a nice way to understand how things works. So you can do this. So as I said, it's a good way to understand how things works, and it's always a good exercise to implement things by hand. But it's not really useful and practical for bigger models. And I like to use that analogy that probably nobody of you writes quicksort anymore from hand to just, you know, to make it more optimal. You just use library that's ready there to do it. You probably wrote one last time in the university to learn how it works, but you don't do it every day. And that's, I did it twice, implemented some algorithms from scratch It was a good exercise, but I wouldn't do it for a production system. I also linked here implementation that Mafi Clerici did, but he did in a very nice functional way, much better than I did it. So when I'm going to distribute slides, you can follow his way of thinking, and I think it's a very nice implementation of linear regression. All right, so but if you don't want to do everything from scratch, you can help yourself with a few things at least. I really like, for example, diffsharp library that's doing automatic differentiation, so it can actually calculate the derivative of any function you pass to it. So the derivative of like linear function I did was very simple. I calculated by hand, didn't do anything, and just wrote it. But if you have like more complicated functions or models, you don't really want to do it by hand or do it like programmatically by yourself. There are like ready libraries to give you derivatives straight away. So that's like one of the helps I like to use. All right, let's go to a bit more mature solution. And Accord.NET is very mature. Its first release was in 2010, but until recently it was like the only way to do machine learning on .NET. It was completely written in C#, didn't have any underlying like C or other low-level dependencies. Has lots of libraries for very specific usages, and I'm going to list them in a moment. Has quite good documentations, but it haven't been maintained that much in recent months. And if it doesn't have library for this thing, it's not very extensible. It's not easy to like build your own calculation models like in TensorFlow, for example. So it's a solid library for the things it can do, but it's not very extensible. So things it can do, for example, it can do classification, which is the type of problem that you say, is this cat or dog or something else? Or regression, which is like inferring new data based on data you have already in your knowledge. So for example, predicting prices of real estate. Clustering is finding similar points of data. So for example, if you have an online store selling some stuff, you can find similar customers and then target some marketing towards them and so on. It has some lower statistical libraries to do some more complicated stuff. And it has also very specific libraries for dealing with images, audio signal, vision, and some natural language processing. So it can quite a lot, but as I said, it's limited to only what it can. So the example of how to do linear regression in Accord, it's pretty simple. Here they're actually using 3 arguments, so we're not going to actually be looking for a line in 2-dimensional space. We're going to look for a plane in 3-dimensional space, but the whole process is very simple. We basically run prediction and then just compare the loss, so basically checking how close we are from the perfect solution, and it's basically it's one line to the actual learning here. So it's quite nice. All right, let's look at Microsoft Cognitive Toolkit, which is also called CNTK, and CNTK is probably the closest option to TensorFlow. It is the kind of library that you build your computational graph, and then you can run this graph to infer the data and so on. It has APIs in Python and C++ and BrainScript, and for a very long time it didn't have C# API, which was very annoying for .NET community because it was like Microsoft product that was targeting mostly Python because it was very well interoperated with NumPy. But after some pressure from the community, they finally published C# API last year. And it's still a bit clunky. It's not very, doesn't offer the same features as Python, and it doesn't give you so nice code, but it's usable and it's getting better. The thing with CNTK, you also need to know what you're doing, so it's very similar with TensorFlow. It's pretty low level, and you have to, you have to know what you want to do. So it's not so easy to just start with it, but if you're some data engineer that's experienced with working with TensorFlow and you would like to do something similar on .NET, that's your best bet. So that's learning done in CNTK. So basically you kind of layer things and add them to the next function and so on. You build computational graph and then you kind of run it in mini batch sizes. So basically you split your input data into smaller batches and run them multiple times. That just makes it easier to run on multiple cores and so on. So you can see it's actually pretty low level. You have to think about those things. So it's not obvious, but if you know what you're doing, it's pretty powerful. And another options to look for is F# bindings for CNTK. That gives you nice F# API. And the code is like closer to Python. They're both very actively developed. One is written by Matthias Brandon Winder and second by F. Varis. I have some preferences. I prefer the first one, and I think it's more actively developed. Basically, the upside is you get a nice code in F# when using it, and I like to program in F#. It's a nicer programming language for .NET, so that's just a good usage for it. All right, the newest child from Microsoft is ML.NET. They announced it at Build this year. It's you can look at it a bit like Keras is to TensorFlow. It's like a set of high-level APIs that doesn't really do any calculation by itself. It just use wherever you have under the hood. So is it either Accord.NET or CNTK or TensorFlow? So let's say you have a Windows machine with CNTK, then it will use CNTK underlying. If you have a Linux machine with TensorFlow installed, it will use TensorFlow on the bottom of things to run the calculations. It has a very high-level API, so it's like more readable, and it's free. It's open source. It's cross-platform, works on everything. I think it's written in .NET Core, and it's like code-first approach. So you write code. There's no like clicky and drag and drop anything. So it's a very good option if you're like a backend developer. You're used to writing code and would like to take your chance at ML.NET. The only upside is I think the current version is 0.7, so I wouldn't use it for production yet. I think it's gonna get there within a year. They're making very good progress on it, and they put a lot of investment into it, and it's actually quite friendly to write stuff. So you define pipeline. So first you like load some text, you label the columns, you categorize stuff and so on. So you first define this pipeline. You define how you want to evaluate the model. So they use, for example, regression model here. And you just run those two functions in your main function, and it's pretty much this. So it's around 20 lines of code to do linear regression, and with a nice definition of pipeline. The only problem with this is this pipeline is not very type safe. So you can, for example, first try to infer from the model before learning it. They kind of don't support the right order of operations yet, but they're working on it. So still you have to know what you're doing, but to lower extent than with other frameworks. Yeah. Now number 5 is Azure Machine Learning Studio, which is a very point-and-clicky user interface. You drag boxes with stuff and connect them with arrows, so you can have nice visualization of the process of your data. You have lots of built-in blocks with algorithms available, but you can also write your own blocks in Python. And when you do this model, train it, you can expose it to the web service, so you can make it kind of, you know, create model and expose it as a web service to your in a like microservice way to other services you run. And it's free to use on the lowest tier level. It doesn't give you super high performance, so it's more for play, but it's a good way to start if you don't want to play. And yeah, for some people, point-and-click interface is a downside, so yeah, your mileage may vary. It kind of looks like this. You have those blocks of data. So like I take my input data, I split data to one that's going to be used for test and evaluation. Oops. I can train the model, score it, so see how good it does, and evaluate on some data. On every step you can visualize your data, so that's, for example, my input data of different properties of red wines. So it gives you like a histogram and list of data and so on. So it's also a nice way to explore your data sets. All right, and for 6 I mentioned a few other solutions that are available, but I haven't have so much to do with them. One is infer.net. It's a quite old library from Microsoft Research, but still they had a new release in March this year, so it seems like it's still developed. I don't know much more about it. I haven't used it. I know it can be used for some machine learning models. FSLab is a like package of like a group of packages in F# ecosystem that's very good for general data science. It's less about machine learning, more about like organizing data in tables, calculating some numerics, doing some statistics, analyzing and charting, creating nice scientific documents and so on. It's kind of around the same topic, but not exactly for machine learning. But it's good to mention. TensorFlow Sharp is a experiment done by Miguel de Icaza from Xamarin. He wanted to port the TensorFlow to C#. He treats it a bit more like as a hobby project. It's interesting to see how he uses like down to the Metal C APIs. But I wouldn't use it on production. It's pretty unstable, and most feature doesn't work. But it's, you know, interesting topic to look into. And Azure Cognitive Services is something good if you really don't want to teach your models, but you want to do something pre-baked for doing some image recognition. So, for example, it has already pre-trained model for image recognition, and you can like feed your set of data. For example, you have data of car pictures, so you want to like train it specifically to recognize cars, and you can take this pre-trained model, augment it with your own data, and get like very specific model for doing some very things that will work for your business. And those are pretty good solution. They're not very malleable. They're the way they are, and if you can make them use for yourself, that's good. But for some advanced usage, it's probably not gonna fit your needs. So they have things for vision, for speech, for natural language processing, and so on. So that was like just overview of what's available. But now you may think, what is good for you? So let's imagine you're a person that like to suffer, and you write your own quickters every day. Then coding from scratch will be probably an option for you. If you like the visual representations and point-and-click interface, and it's tool for you for Learn, then probably Azure ML Studio would be a good bet. If you don't want to mess with training your own models, then probably you should look at cognitive services. And if you're quite experienced, you know what you want and you know what you're doing, then those options are good for you. And if you're a developer, if you have some experience or not really much experience with machine learning, you want to play with it, but you don't mind if it doesn't, it's not production ready, then I would suggest looking into ML.NET. And another thing with ML.NET is that it's actively developed. There's a lot of up-for-grab tasks, so if you're into open source, you can help also developing that library. They're very open for incoming commits. So yeah, that's all. I kind of ran it through very quickly. So that's all from me, but I happily take some questions.
I have a question regarding the last part. So once ML.NET matures enough, is production ready, your recommendation where you propose CNTK, Accord.NET and so on, would also, I understand, include ML.NET?
I think so. I think it's a good natural way because, as I said, CNTK is like very powerful, but you need to mess with a lot of underlying things, like spreading things to go into different core of CPU and stuff like that. And ML.NET does those things for you, and it does it very smartly. So I think when it matures enough, they're going to have like 1.0 things. I would probably use it for a production usage, unless there will be something very specific I'd like to do. But you can still define calculation graphs, so something you do in CNTK. So you can get pretty deep down to like weird network architectures without need to go into CNTK. So yeah, I think so. All right, cool. So you have a longer break now. Thanks for coming.